A todas luces.
Un podcast de Iluminet. Con Jorge Curtidor y Antonio Arellano. Les damos una cordial bienvenida.
A todas luces.
Welcome, everybody. This is our 12th episode of A Todas Luces. We have a very special guest today. Is Dr. Michael Siminovitch. Professor Michael, how are you today?
I'm good. Thank you so much. And yourself?
I'm very good. Thank you for coming here. Can you please start by telling us a little bit about yourself and your main line of work?
Yes, I'm a professor at the University of California, Davis, and I'm also the Rosenfeld Chair for Energy Efficiency, which is an endowed chair that allows me to study lighting energy efficiency. I'm also the director of the California Lighting Technology Center. It's a research and innovation center dedicated to lighting energy efficiency and human factors.
Excellent. So you're just the right guest for our chapter today on color and perception. So, Professor, to start with the subject, what is color? What do we know? And what are the big questions today?
Yes, well, this is a very large topic area, as you know, but very basically, color is a visual phenomena that we as humans perceive from the electromagnetic spectrum coming from the sun. And so we interpret the spectrum differentially, depending upon our environment, as color. And there's basically three aspects of this. And one is the source, the light source, be it the sun or an artificial illuminant. There's the object that's being illuminated, and there's our visual system. And these three factors all go together to define what we interpret as color. And so color is basically a mental sensation where we're processing these three variables together in terms of what is the illuminant, what is the nature of the source, what is the kind of the textural and the reflectance value of the material, and how is our visual system seeing it. And so that's how we define color, as bringing these three variables together as a visual phenomena.
So what is the function of color then? So that's the process, and what is color for?
Well, color is how we interpret the world. And so we look at the world in terms of sort of visual phenomena, in terms of how to navigate and make decisions. And so I sort of break this down into two areas. One is, how do we see the world and how do we interact with it? And that's basically when we're navigating spaces, or we're selecting fruit, or we're deciding on a textural quality for paint, or we're looking at the quality of an interior. This is sort of, we use color as a way of interpreting our real world. And so it's how we interact with the world. So color allows us this kind of very nice kind of differential where we can make choices. Is an apple really ripe? Is a fruit good to eat? Do we like the interaction of colors in an interior? So I sort of lump that together as how we see the world and how we make decisions. But there's a whole other area. And so as an architect and a designer, that's been my primary training, is how do we look at color and how we bring these together in a sympathetic and a harmonious way. So most of us in the lighting design or in the architectural arena, we're very skilled in this. However, there's a whole secondary area related to color. That is, how does a color affect us how does it affect our biology? How does it affect how our homeostasis, how our biology, we call this circadian lighting. This is basically it's our biology, our hormones, and how does the color, lighting intensity and duration, how does that impact our biology? So there's really two broad aspects of color: how we see the world, how we interpret and make decisions. So this is sort of sort of on the task, And then how does color affect our biology and how does it affect our wellness?
How has our understanding of color improved over the last since the invention of colorimetry? Say, what has the big difference from the introduction of this science? And so, what do we know for real? Maybe what are the big questions? What we still don't know about color?
Yeah, well, this is also a huge question. So I think there's first, there's been a lot of work looking at the use of color and how we interpret and how we value the visual environment. And this relates in two ways. One is, first is on color rendering. And this is how natural or real do colors look in our built environment relative to how our visual system is intended to operate. And we call this the color rendering science. And so if we take an apple and we look at the redness of an apple, we interpret this as there's a natural color on this. We want the color to be natural. We don't want there to be distortion or problems with color discrimination. Okay. Now, when we're outside, daylight renders the apple quite well. And so this has to do with principally with the red content of the apple. The apple looks really rich and ripe. However, if we take an apple inside and we're operating under, say, poor fluorescent lighting, the apple's going to look not quite so red and not quite so vibrant and ripe. And so that's a loss in color or in color fidelity. So we call this color fidelity. And fidelity is really a metric that describes how natural or how good does our color look relative to daylight. And so we typically use daylight as our metric. It's a very broad spectrum. It's very rich. So we use that as a common metric. And so there's been a lot of work going into sort of understanding how color rendering is impacted or changed by using artificial illuminant. Now, we know incandescent lighting has got a very good color rendering capability. It's also a very broad spectrum. And so when we look at fruit or we look at woods or skin, we look good under incandescent lighting. However, if you look at fluorescent and some of our inexpensive solid state technology, we typically lose color capability. So color rendering has been a subject of a lot of research trying to understand, one, how do we measure it? Okay. Then two, how do we develop light sources that give us good color rendering? And then three, how do we incorporate that in the design process? How do we enable engineers and architects to do it? So those are the sort of the three principal factors on color rendering. So that's sort of aspect number one. And I'm still dealing now with how architects and designers deal with the world. I'm not talking about the biology factors yet. So the other issue related to color is if you look at how it sort of impacts us on sort of the biology side, there's a couple of different factors. One of the interesting ones, when this was something that was developed at Berkeley more than 30 years ago, where they were looking at the spectral impact on pupil size. So effect of color on pupil size. Now, pupil size is very important. It impacts our visibility, our visual acuity principally. Smaller pupil size, better visual acuity. So you can actually see better. So it turns out that cooler colors in comparison to warmer colors tend to give us smaller pupil size. And the way to look at this is that if you have a room that's illuminated with a very cool Kelvin, a very cool color temperature, the pupil size will be relatively small in comparison to the same space with a warm color temperature. And so naturally, this makes, you have better visual acuity. And so this is something that is generally understood. I mean, if you go outside on a clear blue sky day, you can read very, very easily. Okay, but if you go inside, newspapers are difficult to read because and so as you get older, you get a thing called presbyopia, which is Greek for aged eye, and now you can't concentrate light on the fovea, but with smaller pupil size you can. This is principally a pupil size impact, and this is something that is starting to be generally more understood in terms of lighting complex environments. And of course, the third issue now on color is how does color impact our circadian rhythm? And this has to do with melatonin suppression. So this is both a spectral and an intensity issue. Okay, so turns out that our melanopsin receptor, which is in our eye, controls melatonin. And melatonin is a sort of foundation hormone, allows us to sleep at night. And then in the morning when we get up, the melatonin declines and we go about our day. So it's very important that we have this kind of cyclic variation in both color and intensity throughout the day in order to allow melatonin to build up, but also to suppress it in the morning. The problem is if we're exposed to a lot of blue light in the evening, we tend to suppress melatonin. And when we suppress melatonin, this is when we get biological issues associated with melanopsin disruption. And so this is both a color issue and also an intensity issue where we're looking at both so typically what we need in things like hospitals or homes is we need low level light, and we need the color shifted towards the yellow-red end of the spectrum, something warm color temperatures, 2200 Kelvin, 2700 Kelvin. So we migrate the color. So that's really the third aspect of color, and that's receiving a lot of research now where they're trying to understand what is the intensity, what is the spectrum. But generally, the direction on this research is towards warm color, low color intensity.
So that's like the tendency, warmer colors, lower intensity. That's like for calming us down, like for relaxing environments versus the cooler colors for better visual acuity, right?
Yes, essentially. So the way we always look at this, when I tell my students, if you look outside and you look at the diurnal changes in light characteristics, that's what our biology evolved under. Okay, so if you think about it, our great-grandparents had excellent, superb circadian lighting. They went to bed early. They got up early. They got exposed to a lot of daylight because many of them were working outside, so they had a lot of bright blue light. And then in the evening, as the sun set, we started seeing a lot less light in the home. They were working under very low light conditions and they went to sleep early. So it's a very ideal type of circadian lighting. So there's a lot of people talking about discovery on circadian lighting. Turns out we've had circadian lighting, most of our civilizations have had good circadian lighting. It's only been till recently that we sort of gone against nature and we start putting lighting inside spaces at night. We are disrupting people. We're disrupting. So we need to return to that, where in the evening we have very low color temperatures so that we don't suppress the melatonin and we relax people and we prepare them for sleep. And in the morning, lots of bright light, stimulating, suppress the melatonin, good visibility. You have it exactly right.
All right. And do we need a change in light during the day, or is it enough to get an activation period in the morning and maybe just a short walk to the office, and then you can get locked inside the office without any more like intensity or not caring too much about the color temperature in the office? Is it enough to get an activation period, or do we need like this color tuning during the day? What do we know?
Yeah, it's a great question. So ideally, we as a species were designed for bright white light all day. And so deviations from that are going to naturally have consequences. So the issue now is, well, what are the consequences? And so we're finding now that in office lighting is that the trend has been to reduce. In other words, and the energy efficiency issues have been driving this kind of reduction. And it may be that we're finding we're not getting adequate melatonin suppression. And they've looked at this with children, where they've taken children out of schools, and they've put them outside in a natural environment for a number of days, and under they're outside instead of being in the classroom. And they're finding that their sleep periods are better adjusted, their sleep cycles are better, they're going to sleep earlier, they're waking up earlier, they're more alert. And the takeaway from this is, of course, is that they're exposed to bright white light all day long, as opposed to school lighting, which is relatively low because we're very concerned about energy savings. So the issue is that we more than likely are not getting enough light in our places of work. So if you're in an office or a school or a university, and you're not near a window, you're more than likely not getting enough light. So there's lots of work going in now with the idea of what you just said. Can we give a sort of a periodic kind of setting, like a cup of coffee in the morning, where you give, let's have a blast of light, and then you're okay for the day. I'm not sure about this concept. In other words, I've not seen any data that supports a cup of coffee shot of light is going to do it for you. But for sure, we need to start considering what are the supplemental levels of light that we can put into spaces to ensure that people, because the reality is we cannot all be near windows. It's just that's the nature. For example, we're working on hospital lighting now for nurses, and night nurses don't have the opportunity to be near windows. And so we're looking at the idea of sunlight stations that can be incorporated in the design of hospitals that will allow for adequate brightness during their periods where they're working at their desk or they're preparing notes. And obviously, this isn't going to be for a total 8 hours. It's going to be in snapshots, okay? But the idea is to give them incrementally better light, perhaps for shorter periods, to allow them to what's called entrain their circadian lighting, so that their circadian biology. So somewhere in between the cup of coffee light and all day light is where we're probably headed for a lot of our spaces. But we need to be thinking more seriously about designing our buildings to have access to daylight. There's no reason today why our buildings cannot be totally daylit. I mean, most of our buildings are single or double-story buildings, easy access to skylights, windows, and so we need to have a very solid rethink. There's no reason why we shouldn't have access to daylight. We have been intentionally building buildings badly, and we should stop.
Yes, that's like really going again in the direction of nature, really to where we really come from. Like you said, our grandparents, and working outside and then sleeping in a very dark environment. So yeah, so that should be the direction. Professor, I have one question. You were saying that we don't know for sure if a cup of coffee or what's exactly the approach. Why has it taken so long for us to find out what's the appropriate doses of light? I know this is a very complicated research topic. can you please give us insight of why it's very difficult to understand what's the best lighting in terms of circadian lighting?
Yeah, I mean, there's a lot of good, biological work going on this now, and I think that there's at the scientific level, there's a good understanding of how much light actually causes melatonin suppression. So this is the issue number one. And melatonin suppression is you're exposed to light, and it turns out relatively low levels of light. I mean, typical living room lighting at nighttime is having an impact. So when you're sitting in your living room, watching television, reading a book, talking with the family, that level of light is creating a suppressing effect. It's actually suppressing your melatonin. Now, not totally, but it's having an impact on all of us. And so, people are also working on their computers and on their cell phones, so they're getting additional light stimulation. So we know that light is having an impact and causing circadian disruption. So there's very good science now knowing that even living room lightings, and we know the quantitative values for this. Okay, and so I'm going to go to issue number two. Issue number two is, well, how much light do you need to suppress? Now, there's guidelines on this now in terms of how much melanopic flux do you need in order to suppress. And so there's various organizations have guidelines on this, in terms of how much light do you need and for how long in order to suppress. Our issues is that this is generally understood, and for someone who's asking the question, there are good answers out there today that will say you need more darkness in the evening, and you need more light during the day. Our problem is on implementation. In other words, even though we know this, and a lot of this data is relatively new, I would say within the last few years, we have a generally good understanding that we don't need light at night and we need light during the day. Our problem is lack of implementation. In other words, we don't have the strategies or the education basically on doing this. In other words, I was just recently at our university library here at Davis at 10 o'clock at night. Library was filled with students, all working under very bright, high blue light levels, okay? All drinking coffee. So the issue is should they be doing that? No. Do we know better? Yes. And so as a culture, we need to start putting together the science with the practice. These things need to blend. And generally, we don't do a good job of that, is we don't take the science early enough and move this into practice. Daylighting, and I'll give you another example. Daylighting is called this new strategy, our new way of designing buildings. Well, there's nothing new about daylighting. And we've known for a long time that this is the best way to illuminate our building. But we intentionally deny daylighting in our design process. And we don't reward it, and we don't encourage it, and we don't educate it. And so you'll be hard pressed to find detailed educational programs at universities on how to do good daylighting design. So it's basically an implementation, and I call this issue of education. We need to bridge that gap where we teach our practitioners, our architects, our building engineers of how to do this. And we need to encourage it through policy. We don't have good policy. There is no policy yet on encouraging, healthful building design. Now we're starting to think about that. We reward buildings on energy efficiency, but we don't reward buildings on being healthy, vibrant institutions.
In regards to that, Professor, what do you think of the well standard? Is it going in the right direction?
Yeah, so that's the beginning. And again, we're going to see lots of these kinds of things where, you know, it's the first line in the sand kind of approach where this, you know, you pick a number and the number sort of aligns with the science. You know, it's like, okay, we're going to pick a number and it's going to be, you know, 300 foot candles or 300 lux melanopic lux in order to suppress melatonin, vertical melanopic flux. It's a good first step. It's a good first step. We need to do better. Okay. And, you know, I applaud these folks for sort of being brave and sort of coming out, you know, early in this process. We know them. It was a good first step. We need to do more. You know, and you know, I encourage this kind of activity. We just need to do more.
Okay, Professor, thanks for that. Now, getting a little bit into the measurement part of the color. Now, I congratulate you. We congratulate you for the creation of the opening of the color lab. And so what are you planning to do there? What are the main objectives of the color lab?
Yeah. So the color lab builds on a lot of this interest in sort of developing better insights in terms of how lighting spectrum affect our biology. So the first aspect of this is related to you know, color temperature or the warmness or coolness of color. So we know that the warmer the color and the lower the intensity, the lower the melanopsin disruption. And we know that the higher color temperatures, higher intensity, the more melatonin suppression. Okay, so this lab is we're going to be looking at those issues, but we're taking it one step further. Is what we're going to look at is we're interested in how discrete color impacts mood relative to both preference and biology. And so I'm going to break this down. So we're pretty good today on understanding color temperature and melanopsin disruption. And this could be fairly easily measured with melatonin. Okay, so we can put people into this space and we can do diurnal variations. We know this. Okay, and this is being done many places. But what's not been done is that if you have low color temperature and low intensity, and you look at sort of a spectrum of, or you look at along the black body curve, you look all the way from very warm to very cool, there's a whole sequence of, you know, 2200, 2700, 3000, 4000, 5000, 6000. You look at all these different color temperatures. What is the relative impact of different color temperatures on mood and preference? Okay, so the first one is mood, and this at first order we can look at measurements of cortisol, and cortisol is a stress measure. And so we want to know, and what we're doing in the color lab is we're taking a cohort of students and we're stressing them, and then we're taking the students and then we're putting them into these color lab chamber, and we're exposing them to different spectrum, and we're measuring cortisol before and after. Okay, so we're also in the color lab, we have the ability to produce any color within the CIE color space. So if you want green, purple, blue, yellow, orange, red, we can produce that very easily in this space. We have remarkable color flexibility. Any color you can dream of, we can make. So what we're going to do with these students is, again, first stress them, and then we're going to expose them to a discrete color. And we want to see whether that discrete color will differentially reduce cortisol after their stress. So we stress them, expose them to, say, red, and see if red reduces or increases the cortisol. And then we're going to run a large cohort of students through, and through this, we'll be able to tell if a discrete color causes some impact on cortisol. Now, this is not directly related to the whole circadian issue. That's melatonin suppression. But we're also going to look at that separately. And where this has potential impacts is, think of a very stressful environment like an MRI, or an X-ray facility, or a place where someone's getting a blood sample, or a surgery space, something like this, a place where there's a lot of stress. If you could have a very sort of discrete spectra, maybe it's purple lighting, a low-level purple lighting. If we find out that reduces cortisol differentially, this could have very wide application on spaces where people are in a stressful state of mind. So there's been lots of talk about this. I mean, if you go through the literature, you'll find that people will talk about the use of blue paint or green paint, using green paint in say, prisons or in places, juvenile facilities, places where there's people who have, mental issues, different color. The problem is most of this work has been very subjective, and, they do these kinds of very soft studies, okay? Now, these are good studies, but it's very hard to find sort of detailed evidence-based, biological studies that really look at what's the impact on biometrics, and so we get the question often from architects, well, we have a new health clinic, and what color should we paint the walls? I don't know, and so, we're the so-called color experts, and we're always challenged by this question. And the interesting kind of nuance that's coming along today is we used to talk about paint. Well, the issue today is I tell designers and architects, don't paint the facilities, keep them a neutral white or gray, because you can use light to introduce color. So paint is going to start going away as a variable. We're going to start being able to manipulate spaces with light. I can now, with us, and my color lab is a really good example of this. I can make the walls any color I want. And so I think our ability now with new technologies actually paint walls differentially, both spatially and with temporal variation. So I can put green in the morning and purple in the evening. Now, we need to find out if does that mean anything? Is there any value in that? Okay. So we're kind of looking at some new ideas here. We know for sure that painting a wall with nice low amber in the evening is going to be a good thing. We just haven't got the numbers yet.
So really, really interesting what you're about to find out there in the lab. So mainly mood, definitely changing the stress levels. What about preference? The other topic, do we know, for instance, what's do we have like an universal color that we all like, or does it change all over cultures and all over the world?
Yeah, that's a great question. We're actually looking at parts of that. And preference is always a complex issue, and there's a lot of studies that talk about preference research. And unfortunately, this is fraught with sort of apples and oranges issues, and so as a scientist, we always kind of, it's a little bit difficult, and people do preference studies because they're a little easier to do than the evidence-based, biometrics, issues, because we're monitoring, in our color studies, we're monitoring, cortisol, and we're doing brainwave patterns, and, we're trying to get at that. But we're also doing preference studies where we're asking people, which one makes you more relaxed? Which one do you like? Which one makes you more tense? To see if there's any kind of correlation between the biometrics and the preference. So preference always boils down to a couple of really complex issues. It's preference for what and by whom. Okay, because I may, my preference may be very different from your preference, and also for what, if I'm sitting at home watching television, I may want to have a very warm orange light, but when I'm at work, I may want to have a very bright, cool, bright light. And so it's always preference by who, for what are you doing, and when. And so that's the first slice. The second slice is also cultural variations. And so, you travel different parts of the world, people will have, cultural, they've been brought up with certain colors that have certain intrinsic meanings to them. Now, there more than likely is no ethnic, sort of biological foundation to this. It's not like, Asians have a biological, preference for certain colors, and Europeans have a biological preference for different colors. There's more than likely no biological foundation for that. This is all cultural and what you get brought up with. So that's also tied in with that. Now, we are looking in our large cohort of students, and we're exposing them to different colors. And we're asking them, which ones make you feel more relaxed, and which ones make you feel more tense? And again, we're going to just compare that with our biologics, with our biological data, to see if there's, there might be something there might not be, but we are asking that question. And if you go through the literature, that's the question that gets most often asked, is when people do studies, and there's not a lot of careful studies out there, but the few that I've seen, they'll have different rooms and they'll have different colors inside the space, and they'll ask them, which ones do you prefer? Stuff is very messy, and the answers are usually apples and oranges. And that's the nature of our science. There's a lot of apples and oranges in this business.
Right. Thanks a lot. I'll see you'll be stressing and relaxing a lot of students then in the lab.
Yes.
All right. So to wrap up things a little bit, Michael, I do have a couple of questions. One is,
Please.
Should we be fixated with CRI, or is time for the industry to shift to another metric?
So CRI has been around a long time, and it's basically a metric that describes color fidelity. And it describes very simply how much a light source deviates from daylight or incandescent in rendering a color naturally. And so all this talk or discussion on CRI and TM30 and sort of different vectors for color rendering are basically wrapped up in the same thing. In other words, they're all nuances on different ways to describe it, or on variations on measuring it, but it basically says the same thing. In other words, if you have two different, you have a different illuminant, you compare it to daylight, how well does that render a particular color? And color rendering, whether it's the new CRI or the old CRI, is basically a pretty good first step in terms of understanding how well does an illuminant work in terms of rendering something natural. There's been too much time and attention on this, and it's unfortunately, and it's basically the new metrics are not adding that much more into it. If you've got something, it's basically, there's an awful lot of really poor illuminants out there, and we very simply need to move them into making them good quality. And once you've got a good quality illuminant, 90 CRI above, The rest of it is noise. And we're spending way too much time working on this. If you have something that's 90 CRI or above, it's going to take an instrument or an extreme color expert to tell the difference once you've got something that's 95 CRI. So once you've got something that's good CRI, old metric, new metric, I don't care. It takes a piece of instrumentation to tell the difference. We need to just move away. Our problem was with bad luminance. We need to get broader spectrum LED light sources into our buildings. And that's easy to do. And it's not expensive. And we need to do it.
So it's like the other issue we're talking about. It's more about implementation and education. So this.
Yeah, we need to move to just simply to better illuminance, and they're there, and they're inexpensive, and finding fancier ways to measure that, I think, is not productive. We need to just get rid of the garbage and move into good illuminance and be done with it.
Well, thanks for that. And the last question, Professor, is related to the new Centro de Tecnología de Iluminación, the new lighting technology center here in Guadalajara. So you've been a very important part in this process. Can you tell us about the center? What's the objective? What are you planning to do? How's the progress so far?
Yes, the CTI was put together as a public-private partnership with industry partners, with the university, with your state energy institutions. And it was also an international project with UC Davis. And we collaborated with it on this project. It was a joint proposal. And my work was to be, helpful and useful in terms of working with the professors at UAG to help put this together. And the CTI is basically a research educational institution focused on lighting, energy efficiency issues, and human factors in lighting in Mexico. And it's to work with practitioners, architects, engineers, addressing educational barriers, institutional barriers, and moving good lighting design practice into the mainstream. So it marries a lot of the activities that we're doing at UC Davis, but it's uniquely Mexican, and it's working with Mexican partners and the lighting profession and educational institutions to really develop a center of expertise, knowledge, and innovation in Mexico with a focus on lighting. I think it's really unique. It's going to be the first place in Mexico that's doing this. It's very engaged, and I'm very excited to see the progress that they're making. And I foresee great things happening at that institution, so I'm looking forward to it.
Well, Professor, hope to see you soon around here. And thank you for being out podcast.
My pleasure. Thank you so much.
Esto es A Todas Luces.